The short-circuit ratio, or X over R, is a crucial parameter that indicates the stability of a synchronous generator when subjected to fault conditions. It's essentially a ratio of the synchronous reactance, denoted as X, to the stator resistance, denoted as R. To calculate the short-circuit ratio for a synchronous generator, the formula is X over R equals the quantity XD plus X prime D plus X double prime D and so on, divided by R. In this formula, XD represents the direct axis synchronous reactance, X prime D is the direct axis transient reactance, X double prime D is the direct axis subtransient reactance, and R signifies the stator resistance. It's important to note that the values for XD, X prime D, X double prime D, and any other reactances can usually be found in the generator's manufacturer's data sheets or obtained through specific tests conducted on the generator. To calculate the short-circuit ratio, or X over R, using the data available, firstly, you need to identify the relevant synchronous reactances. This involves determining the values for XD, X prime D, X double prime D, and any other reactances provided in the generator specifications or test reports. Secondly, calculate the total synchronous reactance by summing up all the individual reactance values. The total synchronous reactance, which we'll call X, is equal to XD plus X prime D plus X double prime D and so on. Thirdly, determine the stator resistance R. This value should also be available in the generator's specifications. Fourthly, calculate the short-circuit ratio, or X over R, by dividing the total synchronous reactance X by the stator resistance R, so X over R equals X divided by R. Let's consider an example to illustrate this calculation. Suppose we have a synchronous generator with the following parameters: XD equals 1.0 per unit, X prime D equals 0.7 per unit, X double prime D equals 0.5 per unit, and R equals 0.2 per unit. Using these values, we can calculate the short-circuit ratio, or X over R, as follows: X over R equals the quantity 1.0 per unit plus 0.7 per unit plus 0.5 per unit, divided by 0.2 per unit. This calculation yields a short-circuit ratio, or X over R, of 11. Therefore, for this particular synchronous generator, the short-circuit ratio, or X over R, is 11. The short-circuit ratio provides insights into the generator's ability to maintain voltage stability during fault conditions. A higher X over R ratio generally indicates better stability. Now let's delve deeper into each of the parameters involved in calculating the short-circuit ratio, or X over R. Firstly, let's discuss the direct axis synchronous reactance, XD. The direct axis synchronous reactance, XD, represents the reactance offered by the synchronous generator to a current flowing along the direct axis of the rotor. The direct axis is the axis that aligns with the rotor's field winding. XD is an important parameter that affects the generator's steady-state stability and its ability to supply reactive power to the grid. A higher XD value typically means the generator is less stable and has a lower ability to supply reactive power. Secondly, let's consider the direct axis transient reactance, X prime D. The direct axis transient reactance, X prime D, represents the reactance offered by the synchronous generator to a sudden change in current along the direct axis of the rotor during the first few cycles after a disturbance. This reactance is lower than the synchronous reactance, XD, because it takes into account the effect of damper windings or amortisseur windings, which are shorted conductors embedded in the rotor. X prime D is crucial for determining the generator's transient stability, which is its ability to remain synchronized after a large disturbance, such as a short-circuit fault. A lower X prime D value indicates better transient stability. Thirdly, we have the direct axis subtransient reactance, X double prime D. The direct axis subtransient reactance, X double prime D, represents the reactance offered by the synchronous generator to a sudden change in current along the direct axis of the rotor during the very first moments, typically within the first cycle after a disturbance. This reactance is even lower than the transient reactance, X prime D, because it reflects the initial response of both the damper windings and the armature windings. X double prime D is important for determining the generator's initial response to a fault and the magnitude of the fault current. A lower X double prime D value results in a higher initial fault current. Fourthly, let's look at the stator resistance R. The stator resistance R represents the resistance of the stator windings of the synchronous generator. This resistance is relatively small compared to the reactances, but it plays a role in determining the generator's losses and the damping of oscillations. A higher stator resistance leads to increased losses and improved damping. The short circuit ratio, or X over R, is a valuable indicator of a synchronous generator's performance during fault conditions. A higher X over R ratio generally implies better voltage regulation and stability. However, it can also lead to higher fault currents. A lower X over R ratio, on the other hand, results in lower fault currents but may compromise voltage regulation and stability. Now let's talk more about the significance of the short circuit ratio, or X over R, in power system studies and protection. The short circuit ratio, or X over R, is used extensively in power system studies, particularly in fault analysis and protection coordination. It helps engineers to determine the magnitude of fault currents, the voltage drop during faults, and the appropriate settings for protective relays and circuit breakers. The short circuit ratio, or X over R, is also an important factor in assessing the stability of a power system. A high short circuit ratio, or X over R, can contribute to voltage instability problems, especially in systems with long transmission lines or weak grids. In such cases, it may be necessary to reduce the short circuit ratio, or X over R, by adding series capacitors or other compensation devices. Furthermore, the short circuit ratio, or X over R, is used in the design and selection of generator step-up transformers. These transformers are used to increase the voltage from the generator's output voltage to the transmission voltage. The short circuit impedance of the transformer is typically chosen to limit the fault current and to match the short circuit ratio, or X over R, of the generator. In summary, the short circuit ratio, or X over R, is a critical parameter for synchronous generators that provides insights into their stability, fault current contribution, and overall performance in a power system. Understanding how to calculate and interpret the short circuit ratio, or X over R, is essential for electrical engineers involved in power system design, analysis, and protection. To recap the key points, firstly, the short circuit ratio, or X over R, is a measure of the stability of a synchronous generator under fault conditions. Secondly, it is defined as the ratio of the synchronous reactance X to the stator resistance R. Thirdly, the formula for calculating the short circuit ratio, or X over R, is X over R equals the quantity XD plus X prime D plus X double prime D and so on, divided by R, where XD is the direct axis synchronous reactance, X prime D is the direct axis transient reactance, X double prime D is the direct axis subtransient reactance, and R is the stator resistance. Fourthly, the values for XD, X prime D, X double prime D, and R can be obtained from the generator's manufacturer's data or from tests. Fifthly, a higher short circuit ratio, or X over R, generally indicates better stability but can also lead to higher fault currents. Sixthly, the short circuit ratio, or X over R, is used in power system studies for fault analysis, protection coordination, and stability assessment. And seventhly, understanding the short circuit ratio, or X over R, is essential for electrical engineers involved in power system design, analysis, and protection. Now let's further explore the practical implications and applications of the short circuit ratio, or X over R, in power systems. In power system protection, the short circuit ratio, or X over R, is crucial for setting the operating characteristics of protective relays. Protective relays are devices that monitor the electrical parameters of the system, such as current and voltage, and initiate a trip signal to circuit breakers when a fault is detected. The settings of these relays must be coordinated to ensure that the relay closest to the fault operates first, isolating the faulted section of the system while minimizing the impact on the rest of the grid. The short circuit ratio, or X over R, affects the impedance seen by the relays during a fault. Relays use this impedance information to determine the type and location of the fault. Therefore, accurate knowledge of the short circuit ratio, or X over R, is essential for proper relay coordination. For instance, distance relays, which are commonly used to protect transmission lines, measure the impedance to the fault point. The reach of these relays, which is the distance along the line that they are designed to protect, is determined based on the short circuit impedance of the line, which is influenced by the short circuit ratio, or X over R. If the short circuit ratio, or X over R, is not accurately known, the relays may underreach, failing to detect faults within their intended zone of protection, or overreach, tripping for faults outside their zone of protection. In power system planning, the short circuit ratio, or X over R, is considered when evaluating the impact of adding new generation or transmission facilities to the grid. Adding new generation, such as a synchronous generator, can increase the short circuit level at various points in the system. The short circuit level is the magnitude of the fault current that would flow to a particular location during a short circuit fault. Equipment in the power system, such as circuit breakers, transformers, and cables, must be capable of withstanding the short circuit level. If the addition of new generation causes the short circuit level to exceed the rating of existing equipment, upgrades or modifications may be required. The short circuit ratio, or X over R, of the new generator influences the increase in the short circuit level. A generator with a high short circuit ratio, or X over R, will contribute more to the fault current than a generator with a lower short circuit ratio, or X over R. Similarly, adding new transmission lines can also affect the short circuit ratio, or X over R, and the short circuit level at different locations in the system. Transmission lines with low impedance will increase the short circuit level, while transmission lines with high impedance will decrease the short circuit level. In voltage stability studies, the short circuit ratio, or X over R, is used to assess the system's ability to maintain acceptable voltage levels under various operating conditions. Voltage stability is the ability of a power system to maintain steady voltages at all buses in the system after being subjected to a disturbance, such as a sudden increase in load or a loss of generation. A high short circuit ratio, or X over R, can exacerbate voltage stability problems, especially in systems with long transmission lines or weak grids. In such systems, the voltage drop during a fault can be significant, leading to voltage collapse. To improve voltage stability, various measures can be taken, such as adding reactive power compensation, reducing the impedance of transmission lines, or installing fast-acting voltage regulators. The short circuit ratio, or X over R, is also used in the design of excitation systems for synchronous generators. The excitation system controls the field current of the generator, which in turn controls the generator's output voltage. A well-designed excitation system can improve the generator's stability and its ability to supply reactive power to the grid. The short circuit ratio, or X over R, is one of the parameters that is considered when designing the excitation system. The excitation system must be able to respond quickly to changes in the system voltage and to provide sufficient field current to maintain the generator's output voltage within acceptable limits. In summary, the short circuit ratio, or X over R, is a fundamental parameter that plays a crucial role in various aspects of power system design, planning, protection, and operation. Electrical engineers must have a thorough understanding of the short circuit ratio, or X over R, and its implications in order to ensure the reliable and stable operation of power systems. To further clarify the concepts discussed, let's address some common questions and misconceptions about the short circuit ratio, or X over R. Question 1. Is a high short circuit ratio, or X over R, always better? Answer: not necessarily. While a higher short circuit ratio, or X over R, generally indicates better voltage regulation and stability, it can also lead to higher fault currents, which may exceed the ratings of existing equipment. Therefore, the optimal short circuit ratio, or X over R, depends on the specific characteristics of the power system. Question 2. How does the short circuit ratio, or X over R, affect the selection of circuit breakers? Answer: the short circuit ratio, or X over R, affects the magnitude of the fault current that the circuit breaker must interrupt. Circuit breakers must be selected to have a sufficient interrupting capacity to safely interrupt the maximum fault current that can occur at their location. A higher short circuit ratio, or X over R, requires circuit breakers with higher interrupting capacities. Question 3. Can the short circuit ratio, or X over R, be changed after the generator is installed? Answer: yes, to some extent. The short circuit ratio, or X over R, can be changed by adjusting the generator's excitation system or by adding external impedance to the generator's terminals. However, these changes may have other effects on the generator's performance, such as affecting its ability to supply reactive power. Question 4. How does the short circuit ratio, or X over R, relate to the generator's transient stability? Answer: the short circuit ratio, or X over R, is one of the factors that affects the generator's transient stability. A lower transient reactance, X prime D, which contributes to a lower short circuit ratio, or X over R, generally improves the generator's transient stability. Question 5. Is the short circuit ratio, or X over R, the same for all generators in a power system? Answer: no. The short circuit ratio, or X over R, varies from generator to generator depending on their design and operating characteristics. Larger generators typically have higher short circuit ratios, or X over R, than smaller generators. Question 6. How does the short circuit ratio, or X over R, affect the settings of protective relays? Answer: the short circuit ratio, or X over R, affects the impedance seen by the relays during a fault. Relays use this impedance information to determine the type and location of the fault. Accurate knowledge of the short circuit ratio, or X over R, is essential for proper relay coordination. In conclusion, the short circuit ratio, or X over R, is a complex and multifaceted parameter that plays a vital role in power system engineering. A thorough understanding of the short circuit ratio, or X over R, is essential for electrical engineers involved in the design, analysis, protection, and operation of power systems. By carefully considering the short circuit ratio, or X over R, engineers can ensure the reliable, stable, and efficient operation of power systems. The information presented here provides a comprehensive overview of the short circuit ratio, or X over R, its calculation, significance, and applications in power systems. By understanding these concepts, electrical engineers can make informed decisions and contribute to the advancement of power system technology. The knowledge of the short circuit ratio, or X over R, is not only essential for practicing engineers but also for students and researchers in the field of power engineering. By mastering these concepts, they can prepare themselves for the challenges and opportunities that lie ahead in the ever-evolving world of power systems. The future of power systems will depend on the ability of engineers to design, operate, and protect these systems in a reliable and sustainable manner. The short circuit ratio, or X over R, will continue to be an important parameter in this endeavor, and a deep understanding of its implications will be crucial for success.